In this video, I want to introduce the ideal signal reconstruction, which is also called the sync interpolation. And I want to talk the sampling and the reconstruction using zero order Hold filter. So uh, when we do the ideal signal reconstruction, we start from the discrete signal and we convert the discrete signal to the continuous signal. So continuous signal here, xs t is equal to the summation of n from minus infinity to infinity xn times the delta function. So the delta function is a continuous signal, so xs is a continuous signal, and then we pass the xs into a filter, and we got the continuous time xa. So what is this reconstruction filter looks like? So firstly, when we do sampling, we know the continuous signal the continuous signal in frequency domain is suppose the continuous signal in frequency domain looks like this triangle. The bandwidth of the signal is from minus b to b. So the corresponding axis associated with this xa is just repeated and shift the xa to the to omega s. Here omega s is equal to 2 pi over t. T is the sampling interval. So when we do reconstruction, we don't have xa, but we have xs. How can we reconstruct xa from xs? So we just multiply this low pass filter, and the height of this filter is capital T, and we can by multiply xs and hr, we can reconstruct xa. So hr here equals to t when omega is less than the band limit and 0 otherwise. So because the multiplication in frequency domain is equivalent to the convolution in frequency domain, so the xa in time domain is equal to the convolution of xs in time domain and h in time domain. So the rectangle in frequency domain is equivalent to the sync in time domain. This is called the dialect kernel. Actually, I can also help calculate this. So let's derive the HRT. So HRT, let's do the inverse frequency, inverse Fourier transfer. This is minus infinity to infinity hr times e to the j omega t d omega. So because hr is not 0 only in this range, and hr in this range, hr is equal to capital T. So let's do the j, t, and e, j, t, minus EJT minus. So because this is 2J times sine omega s, because omega s is equal to 2 pi, because omega s is equal to 2 pi over t. So here we can write this is 2J times sine t pi over t, and we add this formula to here, so we get the sine t sine pi t divided by t divided by capital T, the pi t pi t divided t. Oh, I lost, so because here is a t, so we have a t in the numerator, and this is divided t in denominator, so this is sin pi t divided t, pi t over t. So then let's talk the zero order Hode filter. So because in real life we can't construct the impulse response, but we can construct this signal. This signal is we hold until the next sample come in. So here we change the sampling signal delta t to the rectangle signal. This is RT equal to 1 in the sampling interval. So similarly, like using the summation of delta function, now xt equal to the 1 over t xa times the summation of r, and we can also write the xs in frequency domain. So, and because this is rectangle in time domain is equivalent to the sinc in frequency domain. I won't derive this in detail, but after rewrite this formula, we can have this sinc function. So finally we got access in frequency domain using this zero Hode filter. Using this RT, we get the frequency domain. The frequency domain is access in frequency domain is x e to the j omega. This is the x e to the j omega is the frequency with this kind of this kind of discrete signal. They are all points times e to the minus j omega t divided by 2 times the sinc function. So we know the ideal xs is looks like this. So but because here we multiply the ideal x e to the j omega with this sinc function, we can't get the because the sinc function, the gain in different frequency is different. So we can't get we get the maximum gain in the frequency 0, and when the frequency is increased, the gain is not equal to 0 because of this sinc function. So we can only get this kind of curve. So this so actually we still have some wave in the larger frequency, but this will give problem when we reconstruct the. But so because of this curve, when we do the reconstruction, we can't use the rectangle filter. We should use this bowl filter to adjust with the curve. So now HR equal to the EJ omega t time divided by 2 times t divided by, oh sorry, I think there is no t here. There is no t here. Divided by the sinc function. So when we use the zero order Hode filter for sampling, when we do reconstruction, we don't use the rectangle low pass filter. We use this filter.